So let's get started. So just to remind you, the homework 2 will be due tomorrow. So make sure that you submit it. In case you need to resubmit, please send it to the TA because TA is handling all the grading, all the thing on homework. And so today the goal is to finish this topic, and we will start sampling distribution. So basically, we cover almost everything in this topic, but except we have the programming not done. And so let me quickly review what we've been doing. I'm not going to review everything again, but just to highlight what we're doing. The random variable is just trying to put numbers to outcomes, and we have discrete and continuous depending on what kind of number you're putting in. Discrete is usually a natural number, continuous a decimum number. So I'm not going to review the discrete version, rather I will focus on the continuous version. So I quickly jump to the continuous part, where the thing is you can't have the big P in the continuous, so the big F and small f, right, or little f. And the reason why is this is because the big P is not meaningful in this context because of any random variable equal to certain value would be assigned probably 0 because you have infinite many of such cases. So you can't really put anything other than 0. Otherwise, you would adding up problem will add up more than 1. Okay, so that is only meaningful to talk about a range, interval, right? So we always ask the probability that X is belong to certain interval, or otherwise it's not meaningful statement for continuous random variables. And there are several things we learn. We learn uniform. Okay, we learn how to do uniform. It's useful when you talk about things you don't have any idea what's going on there, right? That's how we do the rainfall. All those things we don't have much knowledge unless we are a physics or geologists where we know how things can be done. Then uniform would be the right way to do. And next we talk about exponential, where the exponential is a model that you try to model the arrival time in a with a memoryless property. Okay, where when things hadn't happened yet and the probability remain the same. Okay, so that is the idea, and the main thing you learn from that one is the probability distribution function is like exponential shape. Okay, so that why the name follow the exponential distribution. The next thing is normal. I think I spend a little bit more time talk about this because we'll be doing that in the topic after this one. I mean, for all the rest of the semester. Normal distribution is a bell curve. If a bell in the sense that it is have a symmetric about its mean, which has a parameter mu, and its variance is sigma square. Okay, and do note that the role played by these two parameters will be mu is shifting the graph of the little f, and sigma square is being the how tall is the bell. Okay, and in this particular normal case is the location of the bell and the shape of the bell is independent, right? So the mu and sigma are separate, controlled by different parameters, and that is the main point. And because of this, and then there are many interesting properties of a normal. The first property we know is what we call transformation, where you multiply by a constant plus a constant. A bell curve still remains a bell curve. So it's a very interesting property, right? And that is the reason why we can do the standardization, where you subtract the mean over the standard deviation will give you a mean 0 and standard deviation 1. Okay, and this is very important because of we're looking at the graph, looking at the tables, right? Because of the big F of Z is still without a table, right? Because of the fact that you want to find the F of X, right? And that would be complicated. And that's why you always go to F of Z, right? And F of Z will be something we know very well how to handle, because we just need a single table. And there are actually two versions of the table Z. One is the for positive value and negative value, and they're the same because of symmetry. So you just need to use one of the tables for our purpose. Okay, and these are the examples that you should know, and then probably you would be doing when I assign the next assignment. Then you will know how to handle these problems, right? And this is the examples that have been done, and then you should try to figure out by yourself. If you are unable or you didn't fully follow or you forget, then you try to figure that out. And this is the empirical rule, which essentially said because we're talking about the standard normal, but it essentially means that if the probability that the random variable, if it follow norm bell curve, then it is within 1 SD, right, with 68%, right, with 2 SD 95 and 3 SD 99, right? So actually between 2 SD and 3 SD is very little, right? Actually just only 4%, right? But jump from 1 SD to 2 SD you have 30%, and within the 1 SD you have 70%. Okay, so that is the main thing. The bell, because the bell looks like very fat, very tall at the center, right? So that's why the lot of things are actually within the first SD. Okay, so that's important observation. And actually this is within 2 SD will be mainly the rule actually we're using. Of course, we'll use more precise one later, but this essentially the thing we actually be using for the rest of our class. And this one is just reverse. We're trying to ask the other way around, is if I have is the inverse F, right? F is, you give me the number, I give you the probability, right? It's just reverse, is I give you the probability was a number. So it's inverse of F. Okay, it's an inverse function. Okay, and then we can ask the question, if go back to, if I say X follow a normal distribution with certain mean and certain variance, and then you want to figure out the probability related to X, and how do you do it? It's just you transform it to a Z, right? Because you subtract its mean over the standard deviation, right? And you do the same operation for both sides. This inequality same as this inequality, right? You just subtract and divide, and this thing can transform to Z. This Z is actually a standard normal where you can use a table, okay, or the calculator. And today we talk about Excel formula that tells us how to do this quickly, okay? And these are all extended example, okay? And the last statement we talk about the normal is we were using it, the two property that without proof, because the proof is beyond the scope of a class. But the idea is very simple, but it's also surprising in the sense that if you add 2 bell curve, it's still a bell curve. If you subtract 2 bell curve, it's still a bell curve. So it is not something usual, because imagine the case if you subtract 2 exponential, it's not exponential, right? Because exponential must have a positive number. When you subtract them, it's not positive, right? Subtract 2 binomial is not binomial, because this is not a, you can end up in negative number, which you don't allow it in the binomial, same as Poisson, right? Another hypergeometric. And also the addition is the same, right? When you add 2 binomial, it need not be binomial unless some special cases. Okay, so the bell add up is a bell is a very special case. Okay, so I hope that that is clear. And here indeed we have independent, actually indeed you actually don't really rely on that. But anyway, let's focus on independent because it's the only thing we use in our class. Now the next we'll briefly mention the three special distributions derived from normal. Okay, so we roughly talk about this last class, so we give slightly more detail, but all of them actually will be used in the future classes, so I will just be very brief. Okay, for chi-square, you would not use it because chi-square later you see is defined in the T as the denominator and F as the fraction, both in both numerator and denominator. So chi-square is something we don't use directly in our class. If you want to use it, you will be using what we call the categorical data analysis, but it's not in our course. But if you look at the textbook, not mine, but the standard text, the textbook that designed official textbook, there's a chapter will be using this. But for our course, we're skipping this one, but we still need it because it is a basis for the T distribution and F distribution, which will be used often in the later part in this class, in this course. So chi-square by itself is not difficult to understand what it is, but we don't give the detail. But what it is very simple. We just have a bell curve, standardized bell. It's just like mean zero, sigma equal to 1. And if you look at the bell, right, you can just give you an idea, right? This is a bell curve, right, with mean 0 and sigma 1, right? This is the Z, right? And what we're going to do is if you try to draw number from this bell, okay? It can be negative number, positive number, whatever number it is. You just square it, okay? And what it looks like then will be the chi-square, okay? That's why Z is normal and its square is called chi-square, okay? And that is the meaning of chi-square. And as I said last time, why they call chi-square? Chi is just this notation, chi. And in the old days, they don't really know the distinction between chi and x, okay? Because of typesetting problem, actually it should be x squared. And x is actually referred to the z in our case. So it just z squared. Okay, you can say chi squared actually is z squared. Okay. And here this chi square actually can be you're only one of them, right? That's chi square 1. Okay. It is similar to the idea of Benoni, right? Benoni is just one of them. And if you add n independent of them, it becomes n chi square of degree n. Okay, degree n. So basically just like binomial, right? Binomial is adding n independent Benoni, the same idea here. Okay, just add them up. Okay. Now just like the right, it's the same idea. Okay. And obviously you don't need to remember this, but this is just telling you what they are. Okay. And we will not do any calculation based on chi-square. Okay, we just know there exists certain thing here. Okay, later you will see why we do it, but this will be reserved for the next topic. But this is something you know, chi-square. And the chi-square look like this, the bell shape. So there's something like this. And if you have 3 of them add together like this, you have 6 add together like this. So this is just a graph. You need to just have an interest, but we not use it directly. Okay. So the one we use more directly is the remaining 2, the T distribution, and later is the F. Okay. And later you will see why we use T. Okay. What T is if you have a X is a standardized normal, basically is Z, right? Z. And this is Y is a chi-square degree M, so just like Z1 square plus Z2 square, okay? The M chi-square, right? M standard normal square, right? And what we're looking at is the ratio of these two things, okay? And we have a normal, okay? And we have sum of square the normal divided by m, okay? Average of this, and then the square root, okay? Looks very crazy, and you would not now immediately see why you do it. You will immediately see when I talk about next class, next topic. And we call this guy is called T distribution with M, okay? And it doesn't really matter what it is at the moment, but for you to see what it is it is basically a bell curve, okay? But with some modification. So let's see the diagram. You will see why this is close to bell curve. So look at the uppermost one is the purple one, the golden one or the brown one is t to infinity. So it has many, the parameter m is infinity. And in that case, that is actually z, okay? It's actually z, okay? So if you have the parameter m is smaller, it'll be flatter. So basically t you can imagine is a normal, but you just hammer the head, okay? But not just hammer the head, but you have rip up the tails, okay? So we just basically what we're doing is just like damping here and raising here, okay? And then it becomes t, okay? Let me repeat what I'm saying again. So suppose this is a z, okay? Z look like this, okay? And what should be the t? T would be something like this. You damp the head a little bit, okay? And pulling a tail a little bit, okay? So that's become the t, okay? So that is a, you can imagine it's very close. You can actually see it's very close to the, very close to the bell, not too far from bell. Especially when the parameter m goes up and up and up, then it is approaching the standard normal. Okay, so basically it's just like something very close to standard normal. Okay, that is it. Okay, and it turns out is when the m is big enough, then it's very close to the bell. Okay. And it's also a symmetric one, because same as bell, has mean and median 0, right? And with fat tails, so for fat tails, I mean the excess kurtosis is more than 1. So I mean excess more than 0. Okay, excess kurtosis is bigger than 0. Okay, so kurtosis is more than 3. Okay, so it's a fatter tail. Okay, so that is the only thing you know. And no more than that, okay? Probably you want to ask what is the small f and big F of the t? That even crazier. If you want to take a look, you can look at Wikipedia or other website, you will see the t. And so far, I haven't seen any introductory statistics book actually show you the small f and big F, so I'm not going to bother with that, right? So that would be something like a very close to the bell curve. Okay, that is something you need to know. Okay, we'll use this when bell curve doesn't apply, we use this T curve or a modified bell curve. Okay, you cannot consider it a modified bell curve, which we will be using in the next topic. Okay, very soon. So don't worry, we'll be using it very soon. Okay, so that's that you know there's a something look close to the bell, but we'll be using it. Okay. The very last thing that we will be talking is the F, okay? F is something, again, it's a ratio. The numerator is a chi-square of m divided by m, and denominator is chi-square n divided by n, okay? So it's kind of average of m chi-squared over average of n chi-squared, and that gives you the F, okay? And this is have a two parameter depending on m and n, and probably you will ask what is the use of this, and actually when we do ANOVA, we will be using F, and also when we do the hypothesis testing, we will do F. So F is something we keep using, and probably you want to ask what F looks like, and the shape is not really surprising. It's like either looks like the exponential graph or looks like chi-square, depending on what m and n they are. So it eventually drops down. It's like more like exponential, but sometimes it's more like chi-square. It really depends on the thing, but you can see the ratio of the chi-square must be non-negative. So that is what it looks like. You don't really need to worry about what it looks like, but you can simply think it's downward sloping would be the easiest thing, because sometimes it's like it is best to think it's more like the chi-square. I think chi-square is the better representation of what it looks like. And don't worry, the T and F will be using it very soon. So at the moment, also in assignment, we will just ask you do up to normal. So chi-square, T and F, we can take it as something preview at this moment. Okay, it's okay, you don't know it, but we just put it here because you may want to come back and check out what's going on. Okay, is there any question? Because we are done with the theory part. So if any question, you can just check out the video, okay, in case you don't fully follow. Okay, if there are no question, then I will talk about Excel. The reason we are doing this is because of Excel is convenient to do a lot of calculations. Okay, so we will give you some quick equations that you don't really rely on the tables. You can do quick calculations. Okay, so it should not be hard, just a bunch of functions. Okay, so basically what we need to know for binomial here is just the first one is the most important one. Okay, the second and the third is not really needed. Okay, because this BINOM.DIST is indeed give you the P, okay, the big P. Okay, so let us try to check out this one first. Okay, let me show you this in the Excel. Okay, I open Excel. Okay, what I'm going to do is I first do binomial. Okay, we have n, we have p. Okay, and n is 5. What's p there? Let me check. P is 0.3. Okay, x is 2. Okay, so what we want to show is what is p of x. Okay, so how I hope you can see. Okay, so how can you do that? It's just BINOM.DIST. Okay, and you put the number of you want to do, which is 5. Okay, maybe I just put 5. Okay, and number of trial. No, x. This is x first. Sorry, x is 2. Number of trial is 5. Probability is 0.3. And we're asking, the last one is a little bit trickier, is whether you're cumulative. So if you put false, okay, false will give you the f of x, okay, the p of x, and the true will give you f of x. Okay, so if you want f of x, okay, you will be just do the same thing by normal distribution 2, 5, 0.3, and use true. Okay, so this gives you this is p of 0, p of 1, and p of 2 add together. Okay, I just Okay, I just stop a little bit and see if you have any question here. Okay. So that is how you do the binomial. That is rather fast, right? So in case you don't fully follow, let's go back to the example we have done to see if we can try to check if we're doing the right thing. Okay. I think binomial we have example. Do we? Yeah, with this example. Okay. So same as the NC2, this one. Okay. Actually, let's try to do it by scratch of P of X. Okay. Let's do the scratch, right? With NC2 is combined, right? And then 5/2. Okay. And you multiply by P is 0.3. And you raise to the power 2, right? 2 times success. And is 0.7, okay? Raised to the power 3, okay? So that's the same answer, okay? So this is, you can see this gives you the P, okay? So I hope this is clear what's going on. Is there a question? Okay? So that means that when you do assignment or accept the exam, but otherwise everything can be done rather quickly, right? So this binomial, and let us talk about Poisson. Okay, if there's no problem for a binomial, let's do Excel for the Poisson. Okay, and here in this one, it just basically here I put all the P, then you can actually plot the P of X. Okay, I don't think I need to do it because I think you know how to do the bar graph already. We talked about that. And this is going to talk you about how to plot the F. And again, I think we didn't need to visually do it because I think it's clear what it can be done. Okay. So I want to talk about this Poisson. Okay. So Poisson only have one parameter, which is lambda. Okay. Lambda. So let us see here we have lambda 2 and 5 again. Okay. Lambda, we have X. Okay. I think 5 is here, 2 is here. Okay. So that make us try to calculate P of X. Okay. And F of X again. Okay. So let's see how we can do this. Again, the function is also a Poisson, this Poisson distribution. And we put 2 and put the mean is 5, X and lambda. And then we put false because we're talking about P. Okay. So that is how you get this guy. Okay. And then you also have Poisson.DIST 2 and 5 and true. Okay. And actually the good thing about Excel is you can see we can very quickly calculate the F, right? Because F is something complicated when you try to work on this, because I think in the question here we have a Poisson example, right? Here we have 0.084. So this is what we have. Okay. And the next one is, oh, we don't have that, but you can ask except that probably that 0 less than or equal to 2 customer arrive, then you need to calculate the free entry, right? So that makes things easier. Okay. To show this is true, so let me actually do this guy, right? We will actually derive it from scratch. So we'll be exponential to the negative lambda, so -5, okay, and 5, okay, raised to the power of 2 and divided by factorial of 2. Okay, the reason is because the formula is this, right? e to the negative lambda, lambda x, x factorial. Okay, so that is the formula. Okay, if you remember. Okay, so actually that's why that gives you the same answer. Okay, so that is how you understand what's going on. Actually, I'm trying to verify the formula in Excel. It's very important. Whenever you learn a new formula, you actually need to verify they're right. They need to, this is standard process. Actually, when you go to try to work out in the industry or you work application, you want to make sure you understand the formula. You try to work out an example that actually you know the answer already. Okay, so this is the standard procedure. When you try to implement certain things, you should do the same. This is general rule for programming. So I hope that is it is okay. Okay. So lastly, I think we need to cover the hyper. Is there any question? Is there any question? If no, we go to hypergeometric. Okay, we're talking about discrete first, and then we'll talk about continuous. Okay, discrete. We'll talk about hypergeometric. Okay, I'll upload this file on the Blackboard after the class. Okay. So let's try to see hypergeometric. Okay, hypergeometric. Okay, the formula is followed by XNAN. Okay, so that's why you see why we define XNAN in this context is because of the way Excel is defined. Okay, so it is different from some of the textbook, but this is how we define, right? So let's actually do this hypergeometric, right? XNAN. Okay. Oh, maybe you will just I think I should swap a little bit of the order. Otherwise, you may it is better to have this because what I'm trying to do is try to order the data such that it's exactly same as the order appearance in your function, so that it become easier. Okay, X and A N, right? Remember what hypergeometric is. Out of big N item, you have N of them is good or success. N minus A are called failure or not success. And what you do is trying to draw small n of items. You ask the X is how many of them are, as a random variable, how many of them are successful. So we have 2, 6, we have 2, 6, 4, 30. And this is a number that we use it for our example. So once we do it, we can check out what it is. Okay. So it's hyperlink, HYPGEOM.DIST, and it's 2, 6, 4, 30. Okay. And we have to use false. Okay. And the reason is being that we're talking about the P. Okay. So it's 15%. Okay. And we have HYPGEOM.DIST 2, 6, 4, 30, and false. Okay. Oh, sorry, it should be true. Okay. So that is the answer. Okay. And let's verify this formula. Okay. Whether this is right or wrong. And try to remember what's the formula here. For the P for the hypergeometric, it's actually a free combination, which is n over n, which is you have n thing, you just draw n of them. And the success is there are 4 success over 2. Okay. And you have 26 value item, you need to draw 4. because you are drawing a sample of 6, okay? And n will be just oh, I should be writing the formula, right? It should be a over x n minus a over n minus x, okay? So that's why we have n, or maybe I just write down what are days, right? So this is just 4 over 2, right? 26 over 6 minus 2 is 4, and 30 over 6, okay? So let me do that. That is combine 4, 2 times combine 26, 4 divided by combine, okay, combination 30 over 6, okay? So you get what we want, so we are very happy. So this formula is correct, okay? So I stop a little bit and see if you can follow what we are doing, okay? So hopefully, maybe go around to see if you have a question for the script, because we talk about continuous after that. Okay. If you have the iPad, you can also open Excel and try it yourself, because I guess it's good only if you know how to operate it. Yes. So this say there's 6 good items and 26 bad items. You want 2 of them from the good item, 4 is from the bad item. So it's 4C2 is out of 4 good items, you draw 2 of them. And 26 items, you actually draw 4 because you draw 6 items out. You want 2 of them is good, right? That means 4 must be bad. So basically this question, hypergeometry, again, just saying that you have 30 balls in the box. You try to take 1 ball out and check whether they're good or bad. And you draw, you don't put back, okay? And you're asking, what's the probability that if you draw, here this question, draw 6 balls, and then actually 2 of them are good balls and 4 of them are bad balls, okay? So, okay. Any question? Any question? Is that okay? Is that okay? If that is okay, then I talk about continuous. So what left is the continuous one. Okay. So we'll talk about exponential and normal, just to still chi and F. Also, we'll talk about that. Okay. Exponential. Okay. So do note that when we have continuous, okay. So there's a typo in this slide. This is not a px, it's f of x. Okay, because it's only distribution, just only f. There's no p has minimal because p is always 0. Okay, but we don't need to worry about the f, small f, because we only think it's care about the big F. Okay, if you remember the big F is just this guy, e to the lambda x. Okay, but there's a slight issue about the Excel and the notation in the in that, right? Actually, they use the version is the beta version, which is 1 over lambda. Okay, so that means that you have to input 1 over, okay, as their parameter. Okay, so what I mean is Excel use this. Okay, so that is the one they use. Sometimes you want to use this or you want to use that. I don't know which one is more convenient, but that is the Excel they use. And sometimes other software use other one, so I don't know which one to pick. So that is the notation. But let's try this X and 20. Okay. So let's do exponential. Okay. And X is 10. Okay. And then we have lambda is being 20. Okay. But we are only need the one that used is beta, which is 1/20. Okay. Which is 1/20. Okay. And let's forget we have F. Okay. But we don't really need F, but we just focus on big F. Okay. But the formula is the same, so I just put it here. So your exponential distribution, you put X, okay, and the lambda is actually this guy, maybe just 10.05, and you use the force, will give you the small f, okay, and we use the true, will give you the big F, okay. So only for continuous, you only do the true, right? Because the big F is the thing we care, and it's like 40%, right? So this is exactly what we do when we look at the example with the exponential, right? If you still remember, this is 0.4, right? So let us actually calculate this by hand to show you this is correct, right? Remember how to do the big F, okay? Is the formula is we just have written down, right? It's just 1e to the lambda x, right? So we just 1 minus exponential negative 20 times x, which is 10. 1/20. So 1/20. Okay, so this is the same. So okay. So sorry, I think I should have written this guy. Okay. This is right. So this is right. Did I do that right? Let me check. Sorry. Make sure that I have the same notation I'm using. Okay, I use this. Okay. Okay. I guess okay. Sorry, okay, I think I was confused. So that's actually the lambda. I mean, the formula they use is exactly the same as what we have in the class. Sorry, because lambda is exactly the same as we have in the class. So basically, this guy. Sorry. So this is I mean the formula is exactly e negative lambda x. Okay. So they don't use they still use lambda, not the beta. So just take it back to the statement I mentioned. The formula we taught in the class is exactly the same formula for exponential. They don't use the beta. They still use the they also use the lambda. Okay. So basically just this guy is f, right? So just e to the negative lambda x. Okay. So this is exactly the same formula we are using. Okay. So there's nothing changed. Okay. And That's the reason why we adopt the lambda notation rather than beta notation, which is sometimes used in our textbook. Okay. So finally, I think we should talk about this most important one, the F. Okay. So again, there's a typo for F. So the F. Okay. And the NORM.DIST is something that you will be used very often. The NORM.DIST. Okay. The NORM.DIST. Okay. And normal. Okay. We have, I think we have X. Okay. Mu and sigma. Okay. And do note that they use sigma rather than sigma square. Okay. So we have the question in the I think in the exercise in the slide that we have this. Okay. We don't care about F. Okay. Okay, we don't care about F, so I just don't display the F. It's really not important. But you can just keep it in case you want to know what is it about. Fx. Okay, f of x. Okay. So this is the very important one. It's NORM.DIST. Okay. Put 4 and put mu 16 and 4 and it's false. Okay. And this one is very small. You can see the F is very small. Actually, this is not important because we are actually not using this anytime. Okay. The NORM.DIST. So you can see in particular, this is the F. You don't really do. Why is the case? Let me see. Oh, sorry, it should be 20. Okay. So you can see from this question, the good thing is we actually don't need to convert it to standard normal. Okay, you can see this number is exactly you found in our slides here. Or actually, we have this here. This is asking exactly this question of x less than 16, right? And we just input 16, input 20, input 4, then we're done. Okay. And the reason why, because they actually, or at the background, they actually do standardize and they multiply and they get the same. So basically they do it one step. Okay. And we can't really show you why this is right, because I have said there's no shortcut way to do it. Okay. And let's do the standardized normal. Standard normal, right? Standard normal is just Z, right? Just one, just need not do anything, right? F of Z and F of Z. Okay. And because there's no parameter to put in, that's very simple. Just NORM.S.DIST, and you put 1 and cumulative false. That gives you the small f. And you have NORM.DIST 1, you put true. Okay. It's exactly the same thing you can find in the above. Okay. So this is same as this one, right? Because both of them are just one SD from the mean, right? Because the standardized normal is mean 0, it's 1 away from the SD, right? So same as normal, so they're the same thing. Okay, so these two are very important. Okay, and the last one I want to say for this is we want to look at the what we call the norm inverse. Okay, norm inverse. We actually did it is we asked if the very right hand tail is where left hand tail is 95%, what's the number, right? So the norm inverse, F inverse of F of Z. Okay. We have the norm S inverse 95 in this guy. So what does that guy means? Okay, because it's inverse of F, it's just asking the idea of this. This is actually this is Z alpha C.95. Sorry, C.0. This is Z.05. Reason because this is 95.95. This is 0.05, right? This is C.05. Okay. So, and this area is 0.95, right? And this guy we have shown is 1.65. Okay. Remember how we get this guy? Is to actually look at the table, look at the entry, what is closest to 0.95, we go it back, right? Because remember last time we have 1.64 and 1.65, right? It just remember it's 1.64 and 1.65, and between these two numbers we pick 1.645, right? And indeed it's actually not too far from it, right? It's actually 1.645. Okay, and these are the important thing you need to know. Okay, and we will talk about the quick. We will not do it, but we just show you that the same idea when you do the T. Okay, you have the chi-square, the same idea. We are not going to do T the same. Just T dot and F dot. Okay. I don't think we need to do it right now because we do it later. So the last thing is we try to show you how to construct a Z table. Okay, how to do it by yourself. Okay, and then we have a break. Sorry, a little bit longer than usual, but I guess it's good to stop when we finish the whole chapter. Okay, more quickly we just do the Z table. Okay. So what we do in the Z table here is we have a Z value, right? We have 0, say 0.1, okay? And then maybe up to, I don't know how many we want, but okay. And we want to know what is the F of Z, right? So just norm, just norm S distribution of 0, and we have true. Okay, and actually this actually gives us a table. Okay, so if you go further down, maybe up to 3, right? And that's how you create this Z table. Okay. So this is how you can create any value you want. Okay, it becomes this table. Okay, so that's how you create this one. Okay, and I would like to quickly show you how you can do it with some decimum numbers. Okay, so let me copy this guy, table 2. How you can do that is you have 0.01, okay, and say 0.02, and up to, I guess you want to up to 0.09, okay. And there's a trick how to do this guy is you have to put the absolute address for the A, okay, and plus B1, and you put absolute address for 1, okay, and then you can just click this guy and you do that, okay, then done. Okay, so that's how I do this table. Okay, so but anyway, I put the, so that is the entry for each one. Okay, the reason why I put the $ sign on A, because when you move, you keep the A fixed, right? Because this is looking at the row, and when you move, you also keeping the row, the column, you keep the one fixed, right? You always keep the first row. So that's how you get this one, and you can draw the whole table. Okay, this is the positive Z table. So as I said, you can have as many tables as you want. Okay, so let's have a break, and then we will talk about the sampling distribution in the after the break. So let's have a 10 minutes break. In the meantime, I go around. Let me know if you have any question. I just put it here in case you want to create it by yourself.
I tried it in file and the correct formula. It should be the correct one. You said it was F.INV, and I tried that in the file. Was there only
No need to say true. Yeah, there's no need to say true. Because true is only for I just copy and paste. True is just need to for the distribution. The inverse you don't need to. Good. Okay, thank you. Yeah, thanks.
I don't think it's how to use this formula in Excel, right?
How do I create this quickly?
How to create like rows like sequence.
Oh, you just create one, creates two of them and just drag.
Oh,
Just autocomplete. You create the first three, then you're done. Okay, let me show you. So here you can create 0. Okay, you create this first one 0.01, say 0.02. That Excel will very smartly you keep drag, then done. So just give him the first three number, then you're done. So you don't need to create. So this is 0.1. Okay, even they know how to do it by automatically. So if you do it, highlight it, then highlight it, then just drag.
You can state the number of rows.
Oh yeah. Yeah, but the simplest is just autocomplete. It's just they know how to handle it. But of course you can just even you can just if you want, you can just the easiest is you can say even this plus 0.02. Then you just drag also the same.
I think this is okay. Just like a couple rows.
Yeah. But of course, if you have something like sequence, right, then it's also easy to do, right? If add this guy, right, the sequence, and the thing is like you can just like say this times 2 minus 1, right? You can just drag. You can also add any sequence. So any sequence you type, you can do it.
Sequence formula, I learned it you don't have the sequence formula.
Need not be having there. I mean, you have when you do R, you can do it, but need not.
Because I tried it on a Windows.
Yeah, need not have. But this is the easiest, I think. I mean, you do just express the formula. To me, I mean, this is. Yeah, I don't know, but at least I know just well, either way would work anyway. So I will easily actually this is the one I use in old days, and when they don't have the autocomplete just only appear like less than 10 years ago. So when I was like you, as old as you, I have to do this. So you just add one, and just drag.
It's like the rows you use. I think it's better for like larger amounts of data, so you don't have to drag.
Oh, yeah. But they don't have that for Windows. Yeah, but what can you do? That is what they have. I think they have something similar. But I don't know. But I think you can create some. I forgot. I think you can create some formulas to have a sequence. But I actually seldom use it, so I don't really know, because for me I just use R. I don't really. Okay, let me know, because I seldom. I mean, to be honest, I seldom use Excel. Okay, so since everyone knows how to do Excel, I'm very happy. So I will upload this later after the class, I guess. Maybe just let me upload it, because I guess if I don't do it, just may quickly upload it. Otherwise, I worry if I don't do that. If I don't do that, I worry I forget to do it, and then not good for everyone. Just may quickly do it, and then I will start. Okay. Okay, so it's there, so you can just upload if you check out if you don't know. So here we actually done with the first part of our course. Okay, the first 3 topics are what we call descriptive statistics. Actually, we don't talk about data anyway. Okay, except the first class probably we describe some data, and here we are talking about data. Okay, we talk about sampling. So from the rest of the course, we talk about sampling. We're talking about using data, doing inference, doing some educated guess, educated estimate, educated prediction. Okay, so that is the main focus of the rest of our course. Okay, so you can say this is the main thing we want to learn, because we want to make decision, right? So how to make decision based on data is you have to collect it, right? And then to make decision. Okay. So for our purpose, because this topic you can imagine doing sampling is a huge, large topic. So we focus on something very, very simple. Okay. When we do sampling, there are many ways to do it. Okay. We're focusing on a very simple one, which is called simple random sample. In that case, each element in the population have equal chance being selected. Okay. And each observation is chosen randomly. Okay. And the first 2 is indeed the idea of a simple random sample. Okay. This is what we mean by simple random sample. And in this simple random sample idea, what do we get? Okay. What do we get is the following. Okay. It means that, okay, the observation you get, okay, is actually following what happened in the distribution of the population. Okay, what does that mean? Okay, what does that mean? Okay, it means the following. Okay, so let me have whiteboard. Okay, so you can imagine the following case: your population here. Okay, population is something you want to study. Maybe you want to study the income of people in the village, right? So you can see a village one. Okay, he earns say $1,000, right? And there's a girl here who earned $3,000, right? And maybe there's another old man, okay? He just earned maybe 500, okay? So and so forth. There are many people there, okay? And of course, if you know every single man or woman in this society, right? You can have a bar graph, right? How many they make, right? Or if you can actually draw a polygon, right? And there's no probability here, right? You just plot the data, right? And the question is, if we do simple random sample, okay? Basically what we're doing is every time we go to this population and randomly pick up a guy, okay? And then we don't, of course, we don't draw everyone, right? But suppose the first draw you do is actually picking a random point out of here, right? You randomly pick up a guy from this village, okay? What is this random, you ask him his salary, okay? Or income. So what is the income looks like, right? Actually, what you would do is the random variable, okay, will actually follow this distribution, okay? And the mean of this random variable will be same as if you look at the mean of this data, which is called mu, okay? Look at the variance of this will be the same as the sigma square. Okay, do note that the sigma and this coming from the data of the population. Okay, you look at if you have access to the income data of this village. Okay, look at the mean of this data, look at the variance data. Okay, and if you happen to draw randomly a guy, okay, what you would observe, this is a random variable, right? Because before you draw it, you don't know which one you're going to draw. Okay, if you draw a random guy, actually the distribution of this is exactly what the data is, right? Let me repeat the statement because it's very important to understand what's going on here. Okay, so with the population, okay, and suppose we have all the information, we can have a bar chart or a line plot, right? The frequency chart. Okay, and if we're able to ask everyone, we have this guy. Okay, but if you don't, okay, and we just randomly pick up a guy, okay, and this before you draw it is unknown, right? It's a random variable, depending you draw. If you're drawing things, it's called simple, it's a random sample. Okay, in that case, each draw would have mean same as the population mean, right? And the variance will be same as the population variance. Okay, because you're drawing one number from here, right? Do you see what it is? Because do note that mu and sigma are actually a fixed number if you know what's going on. Okay, but of course if we don't have a data, we randomly draw a guy. This is what we have. Is that clear? Is that clear what's going on? Okay, and simple random sample means the following, because we actually draw 1, 2 up to n. Okay, and we're saying that each draw is independent. Okay, it's separate from the other one. Okay, so what means is you are sampling with replacement. Okay, you ask a guy, you come out, okay, you go in again, okay, even the guy have been asked, you still have the same chance to ask. Okay, so how actually you do it? It's just like these people, you put number to them. Okay, you go in, you roll a die, this is a guy, you talk to that guy. Okay, it's possible that you talk the same guy. Okay, that is simple random sample. Okay, even you've asked him, you may actually ask him again. Okay, so this is, of course, it's not really realistic because in the real world there's a lot of issue. You cannot actually implement this easily because people location, the living location is not random, right? And you used to see people, rich people tend to live in certain area, poor people live to certain area, right? So if you try to do simple random sample, you have to make sure that you have to balance this out, right? You cannot randomly visit a place, right? And then you just ask the income. In that case, you're likely to get more poor people data because more poor people in the society than rich people, right? So you're more likely to reach poor people if you randomly visit places. Okay, so there are some issue there, right? Just like the example, if you do a survey outside the subway station, railway station in front of our school, in that case you are not actually doing a simple random sample. Okay, if you're only interested in CHK student, that's fine, right? But if you try to see is CHK student is a representative of the college student in Hong Kong, probably not, right? I mean, CHK is one of the top 3 in Hong Kong, and some people say top 2. In that case, it's not representative, right? Because, and also if you try to see, I do a simple random sample in this class, right? Probably this is not going to be representative, right? Because you guys are B school, right? Supposed to be more elite than the other faculty, right? So many of you are accountancy, right? Probably also being the even better, right? Or IBBA also very good as well. So it's not it's very representative compared to the whole CHK as well. So that's why it's not easy, okay? But I hope it's clear what it is, right? Because when you do simple random sample, it means that each observation, okay, will have the same mean, same variance, okay, and each observation have zero covariance, so they are independent, and indeed they're independent, right? So it's important because we'll use this property. Okay, so we will be using this term, simple random sample. Okay, and this is the implication of simple random sample, and simple random sample is being defined as this, right? Randomly selected, and each element is selected independently. Okay, equal chance and independently. Okay, not easy because suppose I ask the income. If I have random draw to say, suppose rich people like Li Ka-sing or Ma Yun, right? In that case, they don't answer my question, right? They say go away, right? Very likely. So it's not equal probability being selected because even though your sampling is randomly done, but those people will refuse to answer the question, right? So is that clear? Right? Or if you happen to say you choose a criminal, right? Then probably you ask him what's your income, he will stab you, right? So you can't even finish your survey, right? So it's not easy. I mean, in the real world, it's not easy. Okay, but there are ways. If you learn further, there's a different sampling method. Try to make sure that the sampling is correct. Okay. Is that okay? Now, I think we just formally write this down, right? Simple random sample. If a population of mean mu, variance sigma square. Do note that this is data, okay? This is the data, not random variable. The population have mean, mu, and sigma square. It means that, look, the population, you got all the numbers, okay? And average of this number is mu. And you subtract the mean and take the square. Average of this quantity is the variance, okay? And if we define x1 up to xn, observation from simple random sample, it means that each observation have the same number of the mu, okay? And variance is sigma square. Covariance between two is 0, okay? So do note that this doesn't mean every time you draw can be any number, right? Can be anything, okay? Don't even have number mu, but on average, you will have a mu and the variance same as the sigma square. Okay, is that clear what we're having right now? Because we're actually drawing things from the population, so it would have the same thing. Okay, do note that x1 and xn are random variable. Okay, this observation are random. Before you draw, you can talk about expectation and variance. Okay, after you drawn, then they're not random variable, they're data. Okay, there's a difference there. When we talk about x1 and xn are actually random variable. Okay, so that's why we can say expectation. Okay, now the next thing, okay, I think it's the most important. This is the main thing we focus on. This the whole course is what we call sample mean. Okay, and in the introductory example, we have we have the income of the people. Okay, and what we want to look at is we try to ask people, look at the sample, ask their income, right? And we can, how do we use this data? Okay, we will use this, calculate the mean of this data, right? That is a sample mean. Okay, you just add each observation over n. Okay, and do note that because of each xi are random variable, okay, this sample mean is also a random variable. Okay, what do we mean by that? Because before you draw, you don't know who you drawn, right? Because remember the question, we have a guy and a girl and an old man, right? This is 1,000, this is 3,000, this is 500, okay? And suppose you draw a sample of 2, right? The sample mean depends on who you drawn, right? It happened to be maybe you draw the girl 2 times, right? The salary is 3,000, right? And if you draw the guy and the girl, then the mean will be 2,000, right? If you draw the old man and the boy, then it's 750, right? It really depends on actually who you draw, right? So that's why the sample mean is also a random variable. Okay, it is just depends on what sample you have drawn. Okay, and probably later you will see in the next class, next topic, why we focus on this sample mean, why we care about this guy. Okay, let me tell you why we care about this guy is in the next topic. Okay, probably next week, we will say this x bar we use to estimate the mu, which we want to know. We want to know the actual income in the population, okay? But we don't, unless we have so many resources to ask every single one. Otherwise, we have to rely on sample, okay? Then we will use the sample mean as an estimate to population mean, okay? That is, we want to know, okay? If this data, right? The population mean is, I don't know, 450 divided by 3, right? Is the actual mean is this guy, right? The actual mean is 1,500, right? And so we want to estimate that, right? And then the easiest thing is like, okay, if you have sample of 3, then you are done, right? You ask 3 times 3 guy, then you're done, right? But we don't have these resources. We can only do say 2 n equal to 2. Okay, in that case, you may see, okay, we can end up with different numbers, right? Maybe 70, 750, maybe 1000 can be, depends on what you get, right? But at the end, we will show that the sample mean is a good guess for the population mean. Okay, the income you get from the sample is a good guess from what's happening in the population you care. Okay, so this is something we'll explain why this is good. Okay, we'll explain why this is good, and this will be done in the next class. But this is the idea. The sample mean. Okay, so let me repeat this because each observation by itself is a random variable. This sample mean is also random variable because depend on which sample, which guy you have drawn, right? Suppose you're unlucky, you draw 2 girls from this sample, right? Because random sample can draw twice, right? Then you may conclude the average income is 3,000, which is obviously very wrong, but it happened when you do sampling, right? There's some error there. Okay, so we'll give you idea how to estimate better. Okay, so that would be something it'll be more clear later. Okay, but that is the sample mean. Okay, we'll use it later, but that is the definition. Okay, so the idea is like this. Okay, and what we'll do is we will call the average of sample mean. Okay, because we say this is a random variable. Okay, so it also has the property of expectation and variance. Okay, and what do you mean by expectation? It means the following: you have population, right? Remember what the lead example is: a guy, a girl, an old man. Okay, maybe we need an old woman also as well. Okay, and in that case, depend on what kind of sample you draw, right? Maybe the first sample is you actually draw is a guy and a woman. Okay, then you ask their income, you give the first sample mean, right? And then you can next sample may be an old man, old woman. They give you the other guy, right? And then can be next time maybe a girl and old man and give the other one, right? There are many possible cases, right? You keep doing this, keep drawing, right? And the average of all these possible case, right, will be called the expectation of the sample mean, right? It essentially said you just keep doing this many times, right? And this is what you have. Okay, and the question is, okay, what is this guy? Okay, what is the average of the sample mean? Okay, this is the first thing we want to show. It's one of the most important results. Here is the average of sample mean, which denote as mu of x bar, is actually the population mean. Okay, it means that if the question is if we have a guy, girl, old man, old woman, okay, and if you do many sample, okay, if you do enough sample, okay, average of this sample mean actually give you the actual one you care, the population mean. Okay, because we want to know the average income of the society or a village, but we don't know. We cannot do everyone, right? But suppose if we do sample, it doesn't really rely on sample size n, right? Any sample size is fine. If you keep doing the sampling many times, average of those is exactly what we want to find. Okay, so this is the later we will talk about in next class. Is this is a nice property we call unbiasedness. Okay, so you imagine you keep doing this sample many, many times, okay? And the way you use it is called the sample mean, okay? And average of this will actually get you the answer, okay? And that is the reason why sample mean is good, because hypothetically you keep doing this, okay? And this you get what you want to find, right? So that means that if you just do once, because you only do once, right? In the real world, you don't do many, many samples. You just do one sample. But what you're getting, okay, is a good guess, because you have no reason to believe that it's higher than what you found, and no reason to believe what you lower than what you found. Okay, we'll talk about this more precisely later. But imagine that you keep doing this sampling. You have many, many samples, and this sample mean, you average those sample mean is exactly what you want to get. Okay, so this is what it exactly means. The expected value of the sample mean is the population mean. Okay, so this is a very important idea, and this explains why we use sample mean. Okay, and that is exactly why you learn in the topic 1. We have the mean on sample mean. We don't have the sample mean, right? For the variance, we have the population version and the sample version, which we explain why in the next topic. But the sample, you only have the one thing, just the simple sample, right? You don't have divided by n-1. Just the n is fine, okay? And the reason is because by itself is a nice thing, is because if you hypothetically repeating this many times, you get what you want. But of course, you only do once, right? Okay, is that clear? Or in some scenario, you do many times as well, right? But because in science, right, you do one thing and then some other people repeat what you're doing, and on average, you get what you want to do. Okay, so that is something is good, right? Because suppose you consider a survey by marketing department, right? The marketing guy who just do asking people, right, do a survey. Maybe he just do a survey in January, ask people how people like this product, and in February they do the same thing, right? And if you do enough time, you average those of outcomes, and actually you get what you want. Okay, so that is a nice property here. Okay, but let me talk about the second. I don't have time, but let's look at this example to convince you that probably this example we've done today. So the example, we are going to show you why this is good. Okay, so remember the example we have is a guy and a girl, and an old man is actually right here. Okay, sample of, but we cannot do sample size of 3. If we can do it, then probably we know where we're also going on. Okay, now because we are doing with simple random sample, it actually means that we are doing sampling with replacement. Okay, here we have this guy is earn $1. This guy have $2 in the bank. The old man have $3 in the bank. Okay, and suppose the first we are doing 2 sample. Here means we draw the guy, okay, with the guy again, okay, and with girl and with old man, okay. And if we draw 2 guys the 2 times, then average of the guy income is $1, right? If the first time I draw a guy and a woman, it's $150, right? And a guy and old man is $2. Okay, is that clear? What's going on? Not okay. So what is this entry? This entry means that because we do sample size of 2, okay, means that I draw a guy and a guy again. Okay, why can I have 2 guys? Because we're sampling with replacement. We have a guy, okay, and then I put him back, and I go out and come in, and okay, guy again. Okay, and that happened to be guy, and 2 guys is just 1, right? Because $1. This means that I have a guy and a woman. Okay, a boy and a girl. A boy and girl, boy earn $1, girl earn $2. So it's 150. Okay. This entry means that I have a sample of a guy and old man. Okay. Then $1 and $3 is $2. Is that clear? Okay. So because all 9 entry, I'm not going to go one by one, but all 9 entry have the same probability, right? Because anything is possible equally, right? That's called simple random sample. Okay. In that case, I calculate. You can see the sample mean, right? There will be 1 times 1, right? 1 has probably 1/9, right? Only appear once. And 1.5, you have 2 times. That's why 2/9. Okay. And you have 3 of 2, right? And 2 of 2/9 and 3 of 1/3. Okay. Then the sample mean you just multiply and add them up, right? So you can actually check this is actually 2. So this example shows that if you have this 3 people village and you do a simple random sample of size 2, and the expectation of this sample mean is just 2, which is original because 2, right? Because 1, 2, 3, the average is just 2, right? So that is what I'm showing. Okay. So let me end today, and I'll see you next week. Remember, homework tomorrow due. Okay. If you have a question, you can ask me outside, because I think someone using this tool. Okay. Thank you. I'll see you next week. Enjoy the weekend. Bye bye.